Hi, we're back. So we're going to finish up chapter 7 here with a couple examples. First one is to show that the alternating group on 4 letters does not contain any subgroup of order 6. So remember what chapter 7 is about. Chapter 7 is about Lagrange's theorem. So let's recall a few things. So recall that Lagrange's theorem says if H is a subgroup of G, then the order of H must divide the order of G. However, there's a warning here, right? The converse of Lagrange's theorem is not always true. So CLT is what we call a group that satisfies the converse of Lagrange's theorem. So, okay. But why don't we say it this way? Not all groups are CLT. Okay, so CLT is what we call a group that does satisfy Lagrange's theorem backwards, right? Which says if you have a divisor of the group, then there is a subgroup of that order. Now, so this is basically, this example is saying A of A4 is not CLT. Okay. Remember, the order of A4 is half of the order of S4, the symmetric group on 4 letters. So the order of A4 is 4 factorial divided by 2. That's 12. So 6 would be a divisor, but it turns out we can't have a subgroup of that order. So let's prove this by contradiction. Let's assume that H is a subgroup of A4 with order of H is 6. Okay. Now notice A4 contains 8 elements of order 3. Okay, I could write them all down, I guess, but so there's all the 3 cycles basically will give you 8 elements or 8 possibilities there. And those are all even, so they're all in A4. So we know that there's got to be something inside A4 that is not in H. So let A be in A4, but sorry, let's just say, yeah, with order 3, and A is not in H. Okay. Well, one other thing that Lagrange's theorem says, it says that the index the index of a subgroup, which is the number of distinct cosets of a subgroup H, is just you take the order of the group and you divide by the order of the subgroup. Okay, so this means that the index of the H that we're talking about here must be 2. And of course, this means that then there are 2 distinct cosets, but A is of order 3, so H, A, H, and A squared H are not all different, even though E, A to the 1, and A to the 2 are all different elements. Okay, so one of these has to be equal to, or a pair of them has to be equal. So if H is equal to AH, that implies that A is an H, which we know is a contradiction. Okay, but at the same time, AH can't be equal to A squared H, since that would mean that if I look at what happens when I multiply everything by A on the left, right, this would show that A squared H must be equal to H. But we just said that A squared was equal to A, H. So by transitive property, this once again says that A, H equals H, which is another contradiction. So in the end, right, this says that all elements of order 3 must be contained in H. However, there are too many of them, right? Here we can write them down, right? There's 1, 2, 3, 1, 3, 2, which is the inverse of that one. Okay, 1, 2, 4, 1, 4, 2, the inverse of that. So it's 1, 2, 3, 1, 2, 4, 1, 3, 4. Okay, so 1, 2, 3, its inverse, 1, 2, 4, its inverse, 4, 3, and then 2, 3, 4, and its inverse, 2, 4, 3. Okay, 1, 2, 3, 4, 5, 6, 7, 8. That's too many elements, right? So we know it's a contradiction, another contradiction. So order of H is at least 8, which is a contradiction. Okay. Okay. I think if you guys want to work on trying to show, either prove or disprove, that the dihedral group is CLT, if you can do that and give me your solution, then you can do that for extra credit. So I'll leave that as an exercise. Before I do a classification of groups of order 2p, let me just introduce you to a theorem we're going to use when we do it. So I'm not going to prove this. It's proved in your textbook. But there's a symbol here. If you take two subgroups and then you just multiply them, what I mean by that is I take all symbols that look like this, HK, where H and K are both in the respective subgroup. When you do that, this forms some set in some subset of G. You count them all up, count up the number of elements, it has this formula right here. Okay, so we're going to use that when we prove the following theorem, that if you have a group of order 2p where p is a prime, an odd prime, then either it's cyclic or it's a dihedral group of that order. Remember that the alternating group on 4 letters had order 12. Okay, so that's not of order 2p. That's 2 times 2 times 3. So that wouldn't be in this form, but it's still an interesting application of cosets here that we can do. So let's let the order of G be 2p. If G is cyclic, then G is isomorphic to the integers modulo 2p. We've already shown that, right? If you have any cyclic group of order n, it's isomorphic to Z mod n. Okay, so then we have no elements of order 2p, right? So suppose not. So suppose G is order 2p and is not cyclic. We're going to show that it's isomorphic to the dihedral group. And this, of course, would be easier if we could use generators and relations. We know that the dihedral group is generated by a reflection and a rotation by 360 over p degrees. No, sorry. Yeah, 360 over p. Okay, so anyway, if we take yes, that's right. So if we just rotate by anyway, the generator for the cyclic subgroup of the dihedral group has order p. So take a generator of that. I guess any rotation, and because all right, so d sub p, because p is a prime, is generated by any rotation that's not the identity and a single reflection. So we're just going to show that there is an element of order 2 and an element of order p, right? And then we can show the correct relation that holds in the dihedral group. But let's see how else we can do it without using some of those methods. So since there are no elements of order 2p, let A be a non-identity element in G, and then Lagrange's theorem, or corollary to Lagrange's theorem, implies that the order of A must be a divisor of the order of the group. Okay, so the order of A is not 2p, so the order of A is either 2 or p. So those are both primes, right? So assume that G contains no elements of order p. That means that all elements all non-identity elements are such that they are order 2, right? If that's the case, oops, I need to do that. Then we can find a contradiction here. So then what we have is take A and B are distinct. So let's let A and B be different, right? And order 2, okay. Then A, B is also not equal to A or B. If it were, then it we would have that the other one was the identity. Okay, so that's not allowed. And AB is an element, a non-identity element, right? So that would be order 2. Anyway, we can show that that means that AB squared is the identity. So that means that AB equals AB inverse, which is equal to B inverse A inverse. But B inverse A inverse is equal to A and B. So this is saying that A and B commute with one another. Okay, and we had a homework problem that stated that this means that this is a subgroup of order 4. Okay, but P is an odd prime. So there can't be a subgroup of order 4 in our group. Okay, so this means there must be must be an element of order P. Okay, so now let's assume that G contains no elements of order 2. Okay, so in other words, every element has order P. Okay, well, then let A be some element of order P. Okay, that means the subgroup generated by A has P elements, and the subgroup or the subset of G that isn't in that subgroup has order P minus 1. Right? Order P. No, let me just say it this way. I just need that. So this is greater than 1. Yeah, I think I'm trying to say too much here. So in my notes, I think I have a mistake. This is bigger than 1, right? So it takes, in fact, it equals P, right? So B is in G, take away that subgroup, right? And the order B is P, okay? Now, we know that this subgroup and this subgroup we take the subgroup generated by B, right, and we see what it has in common with subgroup generated by A, it must be this by our theorem below. Okay, so we look at the theorem here, right? This intersection must divide the product of these two things together, right? So okay, so this intersection here, it has to divide the order of this one, which is P. Okay, so this means that either these two subgroups are equal, which is a contradiction, or they only intersect in the identity element. So then but this means that the order of this symbol here, which we know is a subset of G, right? This has to have order A times order B. This is from below, so this formula that formula here that says order of two subgroups, right, multiplied in this way is you take the orders of each one and you divide by the order of the intersection. Okay. And so this one here and this one here both order P, so that's P squared, which is impossible, right? Since that's greater than 2P, right? No good. So this must mean that the order of B is equal to 2. Right? So that means there must be an element of order 2, right? And so G contains an element of order P and an element of order 2. Okay. We need only show that A to the K B is equal to B A to the P minus K. That is the or if you want, just inverse of A to the K. This is the relation for the dihedral group. Okay? But notice that AB, right? This element here is not in the subgroup generated by A, since B is not a power of A, right? So that means that you must have order 2. since any element that isn't in Theorem has order 2 from the previous argument. So this means that AB inverse is equal to B inverse A inverse, which is equal to BA inverse, right? And that's enough, basically, to show what we need to show. Because if we do A to the K, B, right? Once again, that's the same thing. It's not in the it's not in the subgroup generated by A, right? These are the rotations, so this is a reflection. This means that this guy has order 2. And that means A to the K B squared is the identity, okay? Or likewise, A to the K B is equal to its own inverse, which is B inverse A to the minus K, but B inverse is itself. That's what we need to show, right? Okay. And I think this video went a little longer than I expected it to, but you've seen a couple examples where we can use some of this kind of analysis, and it's not obvious, but we're doing some stuff with cosets and then some stuff with playing around with the order of subgroups and how the Lagrange's theorem works for all those things. All right, so good luck and let me know how it goes. Thanks a lot. Bye.